Okay, hello everybody. Welcome back. Okay, so we got something a little bit different this time. So we're kind of stepping away. Well, not really. No, we're not really stepping away from dictionaries and lists and so on because the stuff I'm dealing with today really kind of applies to lists in particular. But yeah, I'm even going to end up dealing with lists of dictionaries today too. So no, they don't go away. This is just something else that you have to worry about. Okay. All right. In this course, what we do is I do a very quick little introduction to the concept of two topics that show up in later courses in programming called searching and sorting. I think it's kind of important that we actually understand what both of these things mean for all of our other programs. Like, for example, when you take the database course, you're going to be doing lots of stuff about searching because you're going to be writing queries. You're also going to learn about sorting and what exactly that means. And I think this is a good place to start. There are certain aspects of it that we don't get into here, like the overall time, something called time complexity. We don't do that. But we do talk today about the speed, or at least the relative speed of the searching algorithms I'm going to give today. All right, so today is all about searching, and strangely enough, I probably have more time in within PowerPoint today than usual because this will be a whole bunch of animations. So I hope the animations end up working out okay. As far as I know, I think they're probably still all right. All right, so here we go. So as usual, I got sections. Yeah, I've got the appendix and so on for containing these things. All right, we're going to be looking two at two different searches today. One called a linear search and another called a binary search. And yeah, there's something about searching complex objects. We'll do examples of that as well. Okay, but most searches fall within these two items unless you're doing something weird called hashing, which is not really part of the course. All right, so here we go. Basic list searching. Well, you know what? These are things that this is actually nothing new. These are things that we have done the entire time. There's absolutely nothing weird that we're going to introduce today. There's a small function down at the bottom called search. I'll write it up again in the interpreter in a few minutes. But basically, when you're searching for things, you want to know one of two possible questions, or well, the answer to one of two possible questions. And the first question is, does a particular element exist in lists? So you have a list of things. Okay, so and yeah, it kind of partially applies to dictionaries as well, but not really because you know with a dictionary, given a key, you can find it really quick. All right, but so I'm just really talking about lists today. So given a list of a bunch of things, does a certain element exist in the list? And another question that you might also ask is, where is the item located in the list? And yeah, if you think about that, we've seen this function or we've seen these operators before and methods. For example, when we deal with the operator in when we're dealing with a list, or we're dealing with the item called contains or index, yeah, that's exactly the types of questions that we're asking. Okay, so the basic algorithm, by the way, still applies. So this is the first thing is going to be like stating the obvious. Okay, and officially it's called a linear search. And I will sort of wave my hands trying to explain why they call it a linear search. But I'm never going to ask you a question about it directly. Okay, but we'll try to get there. But basically, what you do is you start at the beginning of the list and you keep checking. And as soon as you find what you're looking for, then you stop. Okay, let's see. I wanted to go for a couple of minutes and then I want to pause. So sorry, I've got one thing that I have to pause and mention. All right, in section number one today, you will find something called the March 9 attendance quiz. Sometime between 12:45 and 1:45 p.m., please go in and complete that quiz. Okay, don't worry, it's not very difficult. It's got one question. Okay, so don't be freaked out by the question. Hopefully you'll be able to answer it. Okay, I'll remind you again towards the end. Okay, so just I wanted to wait a couple of seconds to make sure I got a few extra people in. All right, so here we go. Back over to here. So over to my searching once again. All right, so what I'm going to do is I got a couple of small animations. So here's a list of numbers. Okay, 69, 97, 87, and so on. I've put 17 of them here total. And basically, I'm asking, okay, if I asked you, if I gave you this list and said, hey, is the number 75 inside the list? Of course, everybody's going to yell out if we're in the class. They're going to say, yes, it is. And if I ask you, where is it? You're going to say it's in position number 9. Usually I get people to yell that out, but yeah, that's pretty obvious. But of course, then the question becomes is, well, how do you find it if you're a computer? Because I mean, we can kind of do this by looking pretty quickly. But basically what we're doing is the same thing the computer is doing, except of course, when you write a program, you have to figure out the logic to actually make it do this. But basically, what you probably do is you probably start from well, I suppose you could start from the other side. Most people probably start from the left side, scan across until they find it and say, yes, it's here. And maybe they have to scan through everything else to find out if there's more, if that's a question. But chances are you probably start from one end and just go until you find it. And what happens with a 45? Well, what you would do, sorry about that, what you'd end up doing is you would start at the beginning and basically you go all the way across to the end. Now, I've put this into an animation. So let's look for 75 in the first one. See, the computer would start by looking at position number 0 and ask, is that a 75? And of course, the answer is no. So then it would go and it would look at position number 1 and say, okay, is this what we're looking for? And the answer is no. And then you check 2, also no, and 3, no, 4, no, 5, no, 6, no, and so on. And then finally, when I reach position number 9, I ask, is this what I'm looking for? At which point you say, yes, I found it, and you stop your search. You either print or return that you found it, or you print or you return the index that you're currently looking at, depending on what it is you're trying to solve. On the other hand, if we try to find something for 45, it's a little bit different because we've, in this case, well, hopefully you've had a chance to skim through the bottom or through the list and you realize that, you know what, the number 45 isn't there. Now, this is an important thing because what is the program actually going to do? Well, it's going to look here, it's going to look here, and guess what? It's going to have to look at every possible number in the list until it finally reaches the end and finally concludes that, oh, it wasn't actually there. Okay, and that is, I don't want to call it kind of a problem, but that's the result of when you do one of these linear searches, is you end up looking through absolutely everything until you reach the end, unless you happen to get lucky and the item is there. Like, for example, if I looked for the number 16 or 97, that would be really simple because just give me a second here. Let's see, got a couple people. So here, I'll just mute you. I don't think you're asking a question. If you are, just leave a chat message and then I will stop. Okay. All right. So here you go. So of course, if you're looking for something like 69 or 797, you're going to find it really quick. If you're looking for the numbers 2 or 39 at the end, well, of course, it's going to end up taking longer. And if you're looking for something that's not there, well, that's actually the worst possible case because you look through absolutely everything. So this is actually something that we do talk about in another course, where we talk about the worst possible cases for algorithms. And the worst possible case in linear search is basically you looked at absolutely everything. And of course, the ramifications for this is if you have 10 million items in your list and you look for something that isn't there, you're going to end up spending 10 million steps, which obviously takes a little bit of time that you have to go through to discover that the item isn't there. And that can be kind of really important depending on the application you're trying to solve. I mean, okay, if we're trying to deal with it, find out if a certain student is taking a certain course, maybe we can live with that. But the example I always bring up is computer games, because everybody seems to understand what a computer game is. And of course, the more time that you're spending searching to find out whether or not, say, the enemy is here, then the lower the refresh rate you'll end up getting on your game. So it actually does have some applications. Now, somewhere in here. Okay, now we can click. Thank you. Okay, so the algorithm that I just described, it actually has a name. And by the way, that is exactly what we've done all semester. So it's not suddenly like, oh, now we've got something new. No, no. The only thing is now we have a name for it. It's called a linear search. All right. Why on earth did they call it a linear search? It's kind of hidden inside the third bullet point. Okay. For example, if you have an array that has 1,000 items and it takes a certain amount of time, if you were to double the size of the array, does it take double the amount of time to find things? And the answer is, yeah, actually it does. So it ends up growing in a linear format. Every time that you double the size of the array, it doubles the amount of time. Okay, and no, that's not important here, but just in case you're wondering why. If you were to draw a graph showing the size of an array versus the amount of time on the y-axis, you get yourself a nice straight line that you could actually make predictions on. But in any case, so that's kind of an overview about why it's called a linear search. More on that if you end up taking the data structures and algorithm analysis course. All right, but in case, here's the real sort of downside to it. If you need to search large lists frequently, it turns out it's maybe not that good of an option. Like, for example, this is starting to become less and less relevant. I used to always describe this as, can you imagine how many things that Google is searching for? Because people are constantly putting things into Google searches to say, hey, give me this. Do you think they used a linear search? And the answer is usually not, because, well, they have millions and millions of websites, well, probably billions of pages. And of course, they're getting billions of hits every second. Now, of course, you're going to say, yeah, but now we're using ChatGPT. Yeah, but you know what? ChatGPT is actually much worse. For example, I hope you guys actually go and do a little bit of learning about how these things work. Basically, what they do is things like ChatGPT are based on probabilities. And what happens is it will look at one word and basically make a prediction about what the next word is supposed to be. And this means that you're searching through very large spaces of data. And of course, you want this to be as quick as possible. So again, linear search is probably not. We've been using the in operator occasionally for lists and sometimes the index method to find out whether or not something is there. Those in the world of lists are very much linear searches. Okay, there's absolutely nothing funny about this whatsoever. All right, now I suppose what I'm going to do is I'm going to introduce to you to one small function. Okay, and inside our interpreter, because I've got something else I have to do in a few minutes. Okay, here we go. All right, here's the first function. No, this is not part of the course. This is just something I'm going to use today. I'm actually going to just drop it down below because it really isn't important what I'm doing. Okay, so you're not going to see it. Don't worry about it. I'll have to go back and see what it is because I forgot what I called it now. All right, but what it is, it says generate sorted numbers. So what I'm going to do is I'm just going to have this thing called values, and I'm going to say generate sorted numbers, and all I need to do is to put in a value, like we'll put in 50 and I'll print the values just so you can see what it does. Generate sorted numbers is not defined. I'm going to have to put it up here, I think. I think this is a restriction. Generate. Here, copy it. Did I misspell it? Okay, good. Oops. No, that's the wrong thing. Sorry, let me get rid of my taskbar. Okay, that taskbar shouldn't bother us anymore. All right, so please ignore that. Okay, whatever you do, please completely ignore that. And sorry, this I actually have to make a small modification as well. Okay, here we go. That will actually make my program a little bit better. Sorry, I forgot to make that change earlier. All right, so what do you think the generate sorted numbers does? Okay, that's pretty easy. What it does is it generates a bunch of numbers that are sorted. And unfortunately, what's going to happen is every time that I run it, I'm going to get different numbers. All right, I was going to kind of hide this up, but you know what? That's fine. I'm going to deal with this. Now, here's what I want to do is I want to find out whether or not a number happens to be inside this list. How do we do it? Okay, for right now, all I'm going to do is just do a simple for loop, right? Well, you know what? I'll call the function because I will need this for later. All right, so I'm going to call it a linear search. All right, when you do a linear search, there are two things that you need. You need the actual data that you're going to search over, and you also have something called a key, and that's what you're looking for. So, as usual, I'm just going to say blah, and I'm going to print the result of a linear search um, within my values for the number 50. Okay, so there you go. All right, so I'm going to generate a bunch of random numbers and I'm going to do a search for them. Now, what does the linear search actually need to look like? Okay, well, exactly what I just said before. What I can do is I can go through each V in data and basically ask the question if V is equal to key, what that means is that I found the answer. If I don't, I return false. So there you go. So I ran it and I didn't find it. Yeah, okay. And guess what? How many items does it have to look at? Well, all 50 of them. Okay, and yeah, okay, in this case, it happened to be there, so my random numbers did contain the number 50. That's fine. Now, what I'm going to do with my exercise today is I'm actually going to search for the value -9. And why am I doing that? Well, because that's definitely a worst case. Because is the number -9 ever going to appear? And the answer is definitely not, no matter what I've got. Now, the reason why I've done this generate is so that I can say increase the number of items if I want to. Okay, and eventually we'll come back and we'll look at these, but we won't do this for right now. Okay, here we go. Let me make 10 that will be fine enough. There you go. So here's 10 numbers. Now, why did I generate sorted numbers? Well, I generated sorted numbers because they have a very interesting property, and that is they happen to be sorted. And when you have sorted numbers, it actually brings us to being able to generate a brand new type of searching algorithm that we haven't looked at before. And this is the next section called a faster way of searching. Okay, so here's the deal with the faster way of searching. If the data is sorted from smallest to biggest, you can apply a technique called the binary search. Here's how it works. You can read the descriptions, but to be honest, it'll make a lot more sense if I show you this. Okay, here we go. This is an array, sorry, a list, wrong course. This is a list with 17 elements, and all of the elements are completely sorted already. Now, the first number we're gonna ask for is the number 75. All right, and again, I would ask the question in the class, I'd say, hey, is the number 75 in the list? Okay, at which point people would end up saying, of course, yes. Okay, just a second. Okay, so the answer would, of course, be yes. And of course, the location is even 10. So, I mean, that's fine. It doesn't really matter. Finding whether or not something exists, finding the location, that's really about the same thing. All right, so the answer is yes, it definitely is there. And if we applied the linear search, what we would do is we would start by looking at the location 0, then 1, then 2, then 3, then 4, then 5, then 6, and blah, 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 blah. And it would end up taking us 10 steps. Okay, well, here's what we're going to do. It's completely different. We're going to start by looking exactly in the middle. Now, how did I know that that's in the middle? Okay, well, it's pretty easy because if you take a look at say this right here, this entire list, the smallest location that I'm looking at, obviously I have to search between 0 and 16. So what I do is I take 0 plus 16, which of course is 16, I divide by 2, that gives me the number 8. And what I do is I ask a question, is that the number that I'm looking for? And of course, well, no, because I'm looking for a 75. However, there's something really important now, and that is because 75 is bigger than 69, is there any chance it would be in the numbers between position 0 and position 8? And the answer is absolutely not. It's not even remotely feasible because the list is already sorted from smallest to biggest. And yes, if you have one element out of place, this whole algorithm doesn't work. All right, so because I'm looking for a number that's bigger than the number that I found, what I'm going to do is I'm going to completely ignore all of the items from position 0 until position number 8, which means that now I'm going to look only between position 9 and position 16. All right, so what's halfway between 16 and 9? Okay, same idea as before. You take the 9 plus the 16. 9 plus 16 is 25. 25 divided by 2 is 12 and a half. Okay, well, we don't have positions or halves, so we always truncate. Okay, so slash slash, and we'll see this. So what I'm going to do is I'm going to look at this position right here, and I'm going to ask, is this what I'm looking for? And once again, the answer is no, that's actually not what it is I'm looking for. But very, very important, the number that I'm searching for is less than this. So as a result, what I'm going to do is I'm going to throw out the upper half of whatever is left. And you see, the only thing left that I have to look at now is between 9 and 11. I don't need to look at anything else because I've already ruled out that there's no possible way that it's there. All right, so I repeat the same thing. So just looking at the area of white between 9 and 11. Okay, 9 plus 11 is 20. 20 divided by 2 is 10. So what I'm going to do is I'm going to check this location right here and I'm going to ask, is that what I'm looking for? And the answer was, yes, it is. Now, think about what I just did. How many numbers did I have to look at to see if it was equal? Well, I needed to look at, let me back up a second. I needed to look at that number, that's one. I needed to look at that number, that's two. And I needed to look at this number, that was three. I only had to look at three values to see if they were what I was looking for. Well, three is a lot faster than 10. I mean, it's a lot less. So therefore, the overall algorithm is also going to end up being, well, a whole lot faster. All right. So three comparisons instead of 11. Okay, I said 11. Yeah, because it starts at zero. That's why. All right, what if we search for something that isn't there? So again, the 45. Okay, well, how does this end up working? Well, exactly the same idea. You start by looking exactly in the middle. The 0 and the 16 added together, divided by 2, it gives you an 8. You look at the 69 and you say, no, no, I'm looking for a 45. Because 45 is less than 69, I'm basically going to throw the entire right-hand part of the list out, and I'm only going to focus now on the white area. Okay, I'm going to repeat it again. All right, what do? Well, we look exactly in the middle. Okay, so where's the middle? Well, it goes between, just give me 1 second. Okay, because I think somebody scheduled a meeting for me at the same time. And anyway, I just didn't go because they should check my schedule. So I figure somebody's going to send me a message saying, where are you? Okay, at which point, then, of course, I got a good excuse not to be in a meeting. Don't tell them that. All right, here we go. So at this point right here, we're going to find a value. We're going to search between position 0 and position 7. Same deal as before. 0 plus 7, that's 7. 7 divided by 2, that's 3, after you throw away the decimal point. And what I'm going to do is I'm going to look at this value right here, and I'm going to ask the question, is that what I'm searching for? And of course, the answer is no, but what I'm searching for is bigger than this number. So basically, I'm going to drop out everything over here in my white area. The spot that's still available is now between 4 and 7. All right, repeat it again. Okay, 4 plus 7. Well, 4 plus 7 is 11. 11 divided by 2 is 5.5. So we're going to search this one and we're going to say, is it the number I'm searching for? Of course, the answer is no, but what I'm searching for is bigger than the 39. So I'm going to ignore the 4 and the 5. Good. So now we're down to two things left, and we have to check exactly what's in the middle. Oh, wait a minute, there's a blank line. No, no. Apply the same algorithm again. You take the 6 plus the 7, that gives you 13. 13 divided by 2 will give you 6.5. And of course, well, truncation, we check this one right here. This is also not what I'm looking for, but what I'm looking for is bigger. So I'm going to ignore this number and everything to the left. Yeah, I know it. There was hardly anything there. All right, so finally I'm left with 7. Okay, same algorithm again. You take the 7 plus the 7, which gives you 14. I know it sounds kind of redundant. You divide by 2 to give you the 7, and you ask the question right here, is this what I'm searching for? The answer is still no, but what I'm searching for is less than this, so I'm going to ignore this element plus everything to the right. Oh, well, you see, now I've got kind of a problem because there's nothing left. Well, if there's nothing left, that means the number I was searching for wasn't there. Now, here's kind of the really important thing. How many values did I end up looking at? Okay, so let me back up again. I looked at the value 69, that was 1. I looked at the value 9, that was 2. I looked at 39, that was 3. I looked at 40, that was 4. And I looked at 55, that was 5. So there are 5 comparisons. 5 comparisons to find out whether or not the item in the list at a particular location was equal to the thing that I was searching for, i.e., the key. All right. And of course, this becomes really important because it's only 5 steps. And in the linear search, this would have been 17. Now, this is where the real power comes from is how many extra steps do we have when you increase the size of the list? It's really quite shocking because even though you might think about it, if I have a list here with 17 items, if I double it to 34 items and ask you how many comparisons does it take, it actually just takes one extra comparison because basically half of the array gets thrown out. Sorry, half of the list gets thrown out each time. I really need to have a big word that says use the word array in this, or sorry, use the word list in this, not the word array. Sorry, I've said before it'll happen because I'm teaching the other course where it's used. The two words mean the same. Okay, so here we go. So we've been able to find out whether or not something was not there in a whole lot less steps. The actual number is can be calculated. Again, this is not part of the course, so don't worry. You're never going to be asked this one. It's based on logarithmic scales. It's really quite phenomenal. Like if you have a list with 1 million items, the number of things that you have to go through is actually like 22 or 23. It's really quite phenomenal. Now, unfortunately, out goes the sort of easy stuff, which is the conceptual understanding, and along comes a very quick little check to find out whether or not we can do an implementation. All right, for me to do this, sorry, you're going to have to give me a second. I'm going to comment out a bunch of other things. Okay, here we go. Let me comment this out and let me just put in some test data just so we can try it. Okay, because I don't like running, trust me, you really don't want to do stuff with random numbers until you have your code working. All right, here we go. So my idea is I'd like to write this thing called a binary search. Okay, same idea, pass in some data, pass in a key. Okay, and again, I'm just going to return blah. Okay, as a temporary thing. Let me get this out of the way. Okay, this way at least. Yeah, okay. I also just wanted to see what I put here for the algorithm for the next one. All right, so let's do the same thing as before. We're going to, but this time we'll return, okay, yeah, we'll return a true or false again, exactly the same. So we'll ask for binary search and we'll ask for the number 40, or sorry, using values and 40. Okay, and of course that should return the value true because it is here. Now, how do you implement this binary search? All right, there's a few different ways. I've given the official one on the next slides, so you can go forward a slide if you happen to have a computer with a separate screen, but I'm going to implement this a little bit differently. This is the usual way. Now, remember what I was doing when I showed you the blue areas versus the white areas? And basically what happens is I started from zero and I went right to the end. The usual way how I implement this is I have a variable called left, which I make equal to zero, and I have a variable called right, which I make equal to the length of the data minus one. Okay, so this would be like the two ends. And what I'm going to do is after I do every search, I'm basically going to move one of the two ends closer. Okay, now I need a loop. Now, I don't know, there's a couple of different ways how this can be done, but I find an infinite loop is actually one of the nicest ways how to deal with do an implementation of a binary search. All right, because what we're going to do is now I can talk about this. Okay, so remember what I did. The very first thing is I took my array, or sorry, my list. Here I go again. And remember what I did was I basically took it. We can start this again for a second. Okay, here you go. So remember what I did is the very first thing that I did is I looked at exactly the middle. Okay, so I need to figure out the middle. Bring up this one and work out the middle. So I'm going to call the middle, once I find my mouse, there we go. I'm going to call it mid. How did I calculate the mid? Notice what I did every time. I took the left value, the lowest possible number I was looking at, position, and I added it to the right side, and I divide it by 2. And of course, I got rid of the decimal point. Yeah, well, that's exactly this floor division stuff. Now, there is actually a value there. And one of the things that I kept asking is if the data at the middle was exactly equal to the key, well, that means that I found what I'm searching for. That's it. Okay. All right. Otherwise, what did I start to do? Well, I started to ask questions. I said, if the data at the mid was less than the key, well, I did something. Well, here, I'll leave in some question marks and I'll just put an else, and that's the other case. Okay. All right. So let's go back and take a look at the picture again. All right. So remember, I'm searching for 79. So what I found inside data at mid was less than 75. So what did I do? Well, I threw out the entire left-hand side. What does it mean to throw the entire left-hand side out? Well, what I'm talking about is, remember, I used to have a variable called left, which is equal to 0. All that I'm going to do is I'm going to move it to 9. And I repeat the entire operation again. I figure out exactly what's in the middle. All right, so if the data that I'm looking for is less than the key, what I do is I move the left to be equal to mid plus 1. Oh, and what do I do in the other case? Well, I move the right and I say that it's right minus 1. The plus 1 and minus 1, yeah, it kind of is important because once you look at the mid position, you don't want to look at it again. And then you just repeat, and it just happens over and over again. This actually works right now. And what I'm going to do, instead of returning true, I'm just going to return mid for a second. All right, so you see, this will be the actual position. So was the number 40 actually in position 7? Yeah, 0, 1, 2, 3, 4, 5, 6, 7. Yeah, it's exactly in position number 7. Let's try to find something else. What if I search for number 5? Well, it should come back and it should tell me it's in position 0. That's good. And if I ask for position 57, that'll be at the very end. All right, position 9, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Yeah, it's right here in position number 9. Okay, there you go. Now, there's only one thing that's left to be done is what if I search for something that isn't there? Well, unfortunately, if I try this, I get myself an infinite loop. The reason why I get an infinite loop is because, well, remember this case, sorry, this one right here, not this one, but this case right here, searching for a 45. You keep cutting it in half each time, but eventually we ended up with this. Well, this would actually show up in my program under one particular case. If the left ever ends up being bigger than the right, that means that I didn't find it. Okay, that's what this means. Okay, so there you go. So that's now the end of it. There you go. So that's the algorithm. What I've done in the slides is pretty much exactly the same thing, but I didn't use an infinite loop. I like the infinite loop because I find it's easier to explain in the classroom because you can say, okay, in this case is what we do, in this case, what we do. The other one, some people prefer the other one because they don't like infinite loops with returns in the middle. All right, so once we're back with this, then I guess we can just turn that back to a true. All right, so there we go. Now, of course, I had a really big kind of claim a few minutes ago, and I said, yeah, I think this thing called binary search is actually going to be kind of faster, like quite a bit faster. And yeah, my calculations, it's like enormously fast. So I suppose what we should do is actually maybe try a small experiment to see whether or not it really is any faster. Because a couple of semesters ago, I had a student after we went through all this, eventually the girl put up her hand and does not make fun of anybody because sometimes it's not always clear. And the question was, why are we doing this? And of course, well, the important thing is, why are we covering this? Well, because binary search is considerably faster, but it would be a lot nicer if I can actually prove it. So here's what I'm going to do. I've got a linear search and a binary search, and I have the ability to make a lot of random numbers, like as many as I want. So here's what I'm going to do is I'm going to say, let's see, I'm going to have values is equal to generate sorted data. All right, and let's see, the first number up is the number of items. Yeah, I start with something small. I'm going to start with 10 this time. Okay, and that should be good enough. I'll just print the values just once to make sure it's all right. Generate sorted data, sorted numbers, sorted numbers. There we go. There's my generate sorted numbers. I don't think I ever need to print them ever again. Okay, because what's going to happen is it's going to become kind of big. All right. If you're, no, I'm trying to remember. I think I might have demonstrated how you measure time before. There's a module called time, very, very useful. And what I can do is I can say time.time, and that will give me a start time. What I will then do is I will do a linear search. Okay, here we go. A linear search for a number. So I pass in the values and I'll pass in something that I know isn't there. Why am I picking it? Because it's the worst possible case. I will have a stop time and I'll print time, and there you go. Now, of course, it doesn't print anything, but what I'm going to do is I'm going to say time for linear search. What you do to calculate the amount of time is you take the stop time and you subtract the start time. All right, and that will tell you. Now, that one looks like it's incredibly, incredibly quick. And yeah, that's because, well, it's only 10 numbers. And guess what? A MacBook, even with a 3-year-old CPU, yeah, it's going to outperform this type of thing. It's not going to take any time at all. All right, so there you go. That's the amount of time for linear search. But you know what I'm also going to do is after I do the linear search, I'm then going to run a binary search. Okay, here we go. So we're sticking a binary search. Okay, and this is for a binary search, and I'll just do exactly the same thing again, binary search. All right, because I want to know whether or not they take, if they really are faster. Now, here's the deal. Searching algorithms, when you're dealing with a really small list of values, it's not really that big of a deal. Things start to become interesting, I think, after you start to get kind of a little bit bigger. So we'll start at 1,000 just to see if there's a difference. Okay, you see, I can't even measure anything. I'll try 10,000. Anything? Ooh, now there's an interesting little problem because it kind of looks like the binary search is actually taking longer. Sometimes this ends up happening. Let's try again. Okay, now okay, well, there's some interesting things that are going on, but generally, if you're talking about a computer with, say, 10 or 100,000 items, that's not very much. And if we start to go off to sort of much, much faster things or much bigger things, we should see a conversion pretty soon. It's one of these things I haven't tried. I hope this is not going to make a liar out of me and it's going to show me that the ooh, that's really terrible. Why is that? Start time, stop time. Am I searching the right thing? Am I calling the right thing? This is almost going sort of backwards. Okay, let me try it one more, then we'll do a quick little search through to figure out have I just called the wrong thing or not. I've got some ideas about what might be going on. Okay, but we'll see what the number comes up to. Okay, so while it's thinking, because I'm sure it's going to take a little bit of time, what goes on? Unfortunately, the world of Python, they actually do a whole lot of optimizations in the background. And yeah, sometimes they will actually make certain slower algorithms actually appear a little bit quicker because of the way things get optimized. I just want to double check and make sure I haven't messed anything up. Oh, I'm out of memory. Ooh, okay. I have to do a slightly different approach. Okay, so I'm going to go back to 1,000, and here's what I need to do. I was kind of expecting this. Okay, how many times have I done the linear search? 5,000 times. Okay, I'm also going to do my binary search 5,000 times. Why am I doing this? I'm trying to slow down the program so that I can get away with smaller numbers. But now this whole thing just makes it look like it's just completely going to make a complete liar out of me by making it look like linear searches are faster than binary searches. Ah, this is absolutely maddening. Um, Binary search. It's going to be one of these things. I'm going to look at this later and I'm going to go, yeah, look what I did. That was absolutely silly. Um, okay, well, okay, you know what? I'll take the hit. I'll blame it on me not trying it in advance. Okay, here. Just a binary search? Oh, come on. You have to be faster than this. Okay, 5.5 seconds. I mean, come on, a linear search searching over something has got to be slower than that. Okay. Maybe what I'll have to do is I'll have to go off. I might have to come back a little bit later. Oh, yeah, it's trying to make a complete liar out of me. Excellent. I honestly think it has something to do with some weird business that's going on inside the interpreter. I've bumped into this a couple of other times, so it's actually kind of not a surprise. But that was not my example that I wanted to show. I wish I could back up the time about 1 hour so I could figure out what was wrong, so I didn't make it look like I was a complete fool here. Anyway, that's all right. Um, you'll have to take my word for it. It sounds like a whole pile of gimmicks. Yeah, I know it really does. Okay. I got one extra thing that I can try. Okay. I don't know if this will make a difference, but I'm willing to try it. Uh, I'm wondering if this is something that I bumped into another time. All right, but in any case, if this doesn't work, then it's fine. We'll just move along. Nothing to see here. Okay. All right, here we go. Here's a linear search and a binary search. Um, I've used something just a little bit different. It might have an impact. I'm not sure. I'm almost doubtful anymore. Okay, yeah, you can see that something's a little bit different this time. I know it didn't make any difference on the binary search. I'm really, really shocked about why it's not working on the binary search. It really doesn't make any sense to me. Um, I'm just completely confused about why it's not actually finding stuff in a binary search faster. Um, okay, I've got one extra thing. You must trust more the interpreter. Okay, well, that's good. Thank you very much. At least I don't feel like a complete fool here, but yeah, actually it does. Okay, I got one extra thing I'd like to do. I'd like to stick a counter in here at 0, and what I'm going to do is I'm going to increment the counter right here, and I'm just going to print the counter. It's never going to be found. I just want to print the counter right here. Okay, sorry. I said this once already. All right, so in any case, 10,000, 10,000, 10,000, 10,000. I shouldn't have 10,000. Yeah, I'm starting to think that my algorithm above isn't quite working as it should. And that would at least explain why it isn't functioning the way I want. Here, let's make it 20 elements. All right. I certainly should not have to look at 20 items before this blows up. There's listen key. I suppose I need to put it up here, do I? No. That'll make no difference if the left is ever bigger than the right. Print counter return false. All right, you know what? I'm going to leave it. Okay. And thank you for trusting me more than this interpreter. I'm sure this will become completely clear once I sit down and say, okay, what is wrong with this? Let me finish up the slide so that at least I don't burn out of time, even though now I just want to solve it. Okay. I promise once I have it fixed, I'll post something into the news items because I'm sure it's something completely obvious. I can actually tell right now that this is not correct because it shouldn't be looking for 20 items. Because if I'm going through mid each time, I should be adjusting left and right each time. I'm sure it is completely, completely obvious. I'll look at it and I'll go, duh. Okay, but let me finish up the slides, and then we'll take a look at it to see if we can figure out why it's gone wrong. Okay, so yes, please trust me more than the interpreter. Okay, so what a silly thing. Okay, that was completely, completely insane. Okay, but anyway, here we go. This is the algorithm. I mean, that's essentially the algorithm that I just wrote because what I did was I said if left was bigger than or equal to right, out I went. I wonder if I've got some kind of a global variable thing going on. It might be. Any case, here we go. One of the things is you might need to know whether or not a list is sorted. And the way how this is done is you go through, you compare each of the items, you compare the position at I to make sure that the position at I is, well, actually, it should be. Okay, if the value at position I is bigger than I plus one, then you return false. So what you're doing is you're going through each pair and you're basically asking, compare 23 to 45, compare 45 to 67, 67 to 89, 89 to 99. If you make it through all of them, then yes, you'd return true. You would obviously need a function like this so that you could decide whether or not to use a binary search, which of course should normally be faster, but for some reason it isn't. All right. But yes, you can actually use this even beyond just very, very simple little lists. You can actually sort or search real data. Um, Sometimes I run this, but I'm not going to because I'm more concerned about the other one. But in any case, here we go, real life data search. So you see, if I had a bunch of students like this, and I ask you, is a certain student here? Like, for example, is the student 6030789 in the list? Well, the only thing that you can possibly do is to iterate through each of them. Okay. And yeah, there would be no other choice other than iterate through each of them. And of course, you'd set up exactly a linear search. Okay, but you can't use the in directly. You can't say if 6030789 is in the list. Well, that doesn't work because when you use the in, sorry, went the wrong way. If the if you use the word in, you'd actually have to know the full thing. And of course, if you know the name of the student and the GPA, then you don't need to look up this information. But then the question becomes is, could I use a binary search on the data that's given? Well, let's take a look. Do you think we could use the binary search on this data? And this data, no, not directly. Okay. And the reason for it is because, well, the students have not been ordered by ID. However, okay, give me a second because do I have it here? No, I don't have it in this one. Where did I put it? Here is the data that I was looking for. Okay, but what if I had this data? All right, so this student data here, we'll just cover up everything so you don't see the mess behind. All right, you see what I've got here. Can I use a binary search for this? And the answer is yes, I can. How can I possibly use this? Well, take a look at the IDs. You see, the IDs are completely sorted. So what this means, if I'm looking for an ID like 6009, because I know I've got students with these numbers because they're coming back, what I would do is exactly the same. You start by looking exactly in the middle and you say, okay, well, what I'm looking for is smaller than this. That means that I can completely ignore all of this and I only need to look between these items here. How do you look into the items here? You look exactly in the middle and you do a comparison again. The only difference is instead of doing the comparison against the entire item in the list, you're working against one particular value or one particular item of the dictionary. And that's the example that I've done here, again, with my botched craziness, um, which I'm really angry and I want to find out. That's why I'm rushing through so I can go and look at it. And all that I've done is exactly the same. I've still got the same calculation where I'm deciding the low plus the high divided by 2, but then I pick out the middle ID by going to the student in the list at the middle ID, and I ask for the ID item itself. And then I start asking the question, if it is what I'm looking for, then fine. Otherwise, I make these other conditions. Oh, now I see exactly the problem. I see exactly the problem. I'm surprised my binary search didn't work. Okay. No, 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 no. It should be okay. It should be okay. I was thinking maybe it was this. I will debug and I'll show you how to debug a binary search. Okay, so there you go. So I can still continue to use a binary search, but of course, the data that you have that you're trying to search on had better be sorted. So, in other words, if I'm searching by ID on this data, it would work. What if I wanted to search by name using a binary search? Well, I could do it, but what I would have to do is I would have to take my list of students and I'd have to sort it alphabetically. So let's see, A, B, C, D, E, F, G, H. Okay, so we're going to have to put in Y. Yusuf would show up at the end. Okay, those M's, of course, have to show up a little bit earlier. So they would go right here. All right, so what do you think about this? Yeah, my data is now sorted according to the names. I could actually use a binary search now on the names, but I couldn't use it on the ID because now my IDs are out. And eventually somebody will usually stick up their hand in the class and they'll say, oh, well, could you search? You could use the binary search on both. Could you have them both sorted? Well, no, unfortunately, you can't have them both sorted because then what happens is you'd end up changing people's names against their IDs, and that's not how it works. So no, you can only have sorting done on one particular property at a time. All right, which of course brings up the important point is, well, if you have a bunch of data like this, how do you put it into the correct order? Well, that's going to be something that we will do next class. Now, there's one final thing that I've left in here. It's called faster searching. I think I've actually demonstrated this back when I was dealing with sets. So I'm not going to repeat it again. But basically, yeah, finding things inside sets is a whole lot faster. All right. Now, that gives me 10 minutes. It gives me 10 minutes to find out what the heck did I do with this crazy business when I was trying to search for things. Yeah, you can tell that I'm completely obsessed by this now because I don't like to leave things alone like this. This is absolutely insane. All right, here's my problem. When I did a search, it actually told me there was 20, and I don't actually believe that. So here's what I'm going to do is I'm going to say values. Okay, just so we've got it. And I'm going to do, once again, a binary search in the issue in line 41. Well, how come you didn't point that out earlier? Yeah, now I see it. All right, great. Thank you. Okay. You know what? I'm going to continue. You're absolutely right. Thank you for spotting it. And yes, you spotted it before I did. The problem is, of course, is I took right and I subtracted one from it rather than putting at the mid minus one. Here's actually what I was going to do. Okay, and I'm going to continue because I think it's useful because this is a debugging technique. And yes, you can see I get stuck with things too like this, even though I'm sure I was 100% certain that it was going to be okay. But thank you. Very good spot for the person who just wrote that in the chat. Okay, binary search. Values. I'm going to search for a minus one, and I will show you how we would have found this pretty quickly. 10 numbers would be more than enough. All right, instead of printing this, this is a very typical thing that I would end up printing. I would print the left, the right, the mid, and the data at mid. Okay, just so I can see what's going on. And I would have started to ask the question. Okay, in fact, you would have seen, I would have found it very quickly. You see, this is what the left and the right were the first time. All right, we looked, we found a number 20. I was looking for a minus one, and this number right here came down by one. And of course, well, it shouldn't have come down by one. It should have come down to three, which is exactly the mid. Oh, there we go. And finally it. Okay, and again, as I'm shaking my fist at anybody who knew and didn't tell me, okay, it's fine. All right, but honestly, I've said this before. Yeah, I used the printing to find out. All right, I believe now this might actually work. I don't need my counter. I became very suspicious about the counter because the counter should have been done really quickly. Okay, and finally, doo-doo, here we go. No, no, come on. This, and this, and this, and this, and this, and this. All right. 5,000 times. Yes, I will do it 5,000 times. No, you know what? I'll do it just once because I think I can get kind of a big enough number now. It might actually make sense. All right, really small numbers, exactly what's going to happen. 1,000 elements. Okay, that's starting to behave a little bit more like I was expecting. What about 10,000 items? Okay, also, let's make it 1 million. Okay, one shot at 1 million. All right, so the binary search ended up taking zero point 0.2 seconds. Or sorry, the linear search was zero point 0.2. The binary search was still measured at 0. Okay, let's go for one more. All right, that should be around 2 seconds for the first one. Hopefully we get something other than a 0 for the second one. Or sorry, 20 seconds, I guess. Okay, here we go. 2 seconds. And you can see that, yeah, the binary search is still hasn't even given me anything. If I were to repeat this over and over again, 100,000. All right, here, let's repeat it 5,000 or 500 times will be good, I think. Maybe this will give me just some numbers other than just 0. Okay, there we go. At least now this is starting to act the way that I was expecting. Yes, that is actually it. All right, so sorry about that. And thank you for tracking that down. I told you it'd be one of these maddening things I would look at and go immediately is like, whoa, what have I done? All right, perfect. All right, so 5 minutes to spare. Thank you for pointing that out. We would have found it with the printing. Okay, I mean, we would have found it. So a very quick print, but it just goes to show you that sometimes if you're doing something off the top of your head and you think you've done it, you can get yourself into trouble. Okay, that wasn't my intention, by the way. I mean, that really was a mistake on my part. All right, but great. So we have it, and at least I've managed to prove that, yeah, it is faster. Eventually, if it's implemented correctly, it is faster. Okay, excellent. All right, guys, that is all that we're going to do today. So, a couple of things. First of all, okay, remember this little attendance quiz? Sorry, I can't bring it back now. Right there. Okay, I'm not actually logged in. Please complete that over the next 4 minutes. This week, quiz number 3 is being done through Lockdown Browser with Respondus Monitor that requires a web camera. If you're having issues with your web camera and just can't do this or whatever other reasons that we've got, just let your lab instructor know. And what we're going to do is anybody who can't finish it up, we will allow you to finish this once we get back onto campus. I recommend, if possible, to try and get the quizzes out of the way even while we're online, because this way it'll be like a day that you can work in the labs on the lab questions rather than doing like 5 quizzes in a row or something. I hope it doesn't come to this, but unfortunately, I'm kind of guessing that we're here for the entire week at least. All right, that's it. I better leave you 3 minutes to go and answer your very difficult attendance quiz. Okay, yeah, don't freak out by that. Okay, I'll see you guys on Wednesday, and hopefully I don't mess things up, and we'll actually be able to sort things. Yes, a very difficult quiz, and no, this will not be the equivalent difficulty on the final exam. Sorry.
Thank you so much, Professor. I wasn't expect this hard, to be honest.
Okay, that's all the time. I will stop this so I can put up a lecture recording. And apparently I have a lot of hard work to grade a quiz now.